and he has completed his BTech in Manufacturing Engineering in 2001 from NIFFT Ranchi, and he completed his Masters from the prestigious institution IIC Bangalore in 2003, and did his PhD from the same institution in 2008. Also, he has done his postdoctoral fellowship at École des Mines, Nancy in France, and he has got awarded the Marie Curie Fellowship at the University of Southampton in UK. Also, his various academic honors include P.K. Kelkar Young Faculty Research Fellowship position at IIT Kanpur. Also, IEI Young Engineers Award, Britain's Young Engineers in UK, YIM Boston Award 2011 in USA. He has published more than around 100 peer-reviewed journal papers and around 100 conference papers. At IIT Kanpur, he is leading the additive manufacturing group. His areas of interest includes metal additive manufacturing, melting or solidification modeling and experiments, multi-stage computational heat transfer and fluid flow modeling, thermal spray, surface coating technologies, and phase change based energy storage technologies. So let me directly invite Dr. Arvind Kumar for the valuable session. Thank you.
Sir, yeah, please turn on your mic, sir. Yes.
Thanks for the introduction, and I particularly thank Dr. Shanmugesh for inviting me to deliver a lecture in this interesting short-term course, which is actually IoT-based manufacturing and design challenges. So, in this talk, I looked at how this 3D printing and additive manufacturing technology can enable IoT-based manufacturing. So my current talk is actually based on this. Can you see my shared slide?
No, sir.
Just I am sharing it. Just hold on. Is it visible now?
Fine, sir.
All right. This talk will describe to the participants how additive manufacturing, particularly on metals, can contribute to IoT-based manufacturing. In this first slide, you can see on the right-hand side the process of metal additive manufacturing based on metal powders, and on left side it is an animation showing say for example how various connected devices based on cloud can work in a synergistic manner. This is the idea to integrate such flexibility of IoT based systems into metal additive manufacturing. So before I start, I just like to show you the place from where I come. This is Indian Institute of Technology, Kanpur, and I work in the Department of Mechanical Engineering. This slide shows you some collage of different architectures and buildings within our campus. Then my lab is additive manufacturing lab, and as already introduced, the kind of research work we are involved in, and this is our small group. We will see more details about our group and activities at the end. So the content of today's talk, I would very briefly browse through some topics like Internet of Things, Industry 4.0, additive manufacturing, and then the major portion of the talk will cover how additive manufacturing can contribute to Industry 4.2 and IoT based manufacturing. So I'm sure you will keep hearing the initial description throughout this course. So to tune in the actual topic, I will also introduce you with the initial topics, but very briefly. So Internet of Things, right? Very classical example comes like say these days many of us use something like Alexa or Google Assistant at our home to command that our virtual personal assistant to operate some of the jobs. Like say we have Alexa at our home, and if our electrical switches and electrical appliances are smartly networked, then we can instruct Alexa, for example, to dim the dining room lights. Okay, and after hearing that, Alexa will assist us by actually performing this job. Same way we can ask different aspects, turning on the light, locking the door, or switching on, switching off some appliances, to play music, and even to answer some of the basic questions, right? So the idea, we know that how this system works at the background, right? I will also browse through that very briefly. So what we know that just 5 years ago, Alexa would have been an actual person, right, who could do all the jobs for us. But today, it is one of virtual personal assistant, uh, which are actually connected through vast networks of interconnected smart devices. And such smart devices, for example, now they are in billion in numbers throughout the world. And the Internet of Things, called IoT, is one of the recent innovation that has taken the world by a storm. And how it is defined as a concept, IoT is very simple. Okay, basically here we connect devices to each other and the internet by building sensors and transmitters into them, so that they can communicate and collectively serve a function better than if each was operating individually. So this is the basic definition. Now this is some interesting data we have. uh, like say Internet of People, this is a data from 2010. You can see various people connected through internet, right? And we have world population of, say, that time it was 6.8 billion, and that time the total number of connected devices were something about 12 billion. It is approximately 1.8 times of the world population. Now by the year 2020, if we talk about Internet of Things, right? So here now we have, you can see, just let me put the laser. You can see we have people connected to internet, then things connected to internet, and then things connected to things, right? So by now we have a population of, say, 7.6 billion, and now total number of connected things, right, in this manner, which constitute of all these three aspects, we have 212 billion, about 30 times of world population. So you can see internet is a wide platform where all these connections can be possible. We could have Internet of People, then we have Internet of Things, and slowly now, particularly for industrial application, we are evolving industrial Internet of Things, right? So we all know that how Alexa kind of a smart, services work, right? We have that device at our home, right? And we can command the device for various actions, like say I am commanding it with turn on bedtime light. Okay. Then Alexa services, it is basically a smart home API. Okay. And after that, to operate the directives uh, based on turn or request, it looks at a smartphone skill developer kind of system, where various skills are being registered time to time, and it is being updated, and they are connected to a device cloud, right? So based on our command, Alexa internally assess that how to best perform that command, and then very quickly, using all these connected devices and connected commands, it turns out that it will operate your command, and that will exactly, and it turns out to be very quickly, without taking much time. And then suppose it turns out your bedroom lights. Okay. This you can do even home or office, and both can be connected together, and this system is eventually connected to internet. So this is how a system on internet of things work, right? This very basic thing, I'm sure you all know about this. After this very basic introduction, I would also briefly touch upon Industry 4.0. So the background I wanted to give, like say, Industry 1.0 started in 1780s, and that time it was based on mechanization, and particularly to steam power and weaving loom, okay, for textile industry. And then Industry 2.0 started in just about 100 years later. It is basically innovation in assembly line and mass production system for that, and then electrical energy. Then Industry 3.0, it started in 1970s, and here we have basically involvement of automation, computers, and electronics. And now Industry 4.0, which is today, it is, people are saying this as based on cyber physical system, Internet of Things, networks, and how it can drive the industrial revolution, which we call typically fourth industrial revolution. So if we further see in Industry 4.0, there are emerging new technology are inbuilt in this. For example, we have Internet of Things, then additive manufacturing and digital twin, cyber security, robots, augmented reality, and all these are part of Industry 4.1, and we can clearly see that additive manufacturing is one of the prime player here, right? And if we try to combine this additive manufacturing based on Internet of Things, then we are trying to couple these two together and to provide us even better results. So Industry 4.0 is the use of a range of digital technologies to enhance the performance, output, monitoring, and control of manufacturing processes. Okay. And typically we have two aspects into this. One is a smart factory, and other is manufacturing of smart products, right? And as I mentioned, in overall sense, Industry 4.0 include various aspects like process automation, real-time process monitoring, additive manufacturing or 3D printing, and augmented reality visualization. Now I like to mention one thing. Monitoring and control based on Internet of Things can provide us increased industrial efficiency. So recent advances in sensing and communication technology can enable us to better understand our production and manufacturing processes, and we can identify the process bottlenecks beforehand, and thereby can implement predictive and preventive maintenance. Further, sensors can provide live updates on our production processes, as well as identifying when the tools are need to be changed or tools require maintenance. So these are the important aspects that can be applied to any industry, and particularly manufacturing industry in particular. So after this brief introduction about IoT and Industry 4.0, I would like to start with additive manufacturing. Okay, and then here we'll see the idea is that to understand how it can contribute to Industry 4.0, I will introduce you with basic introduction of additive manufacturing, then its benefits and industrial application, and challenges and future pathway. And then we could see in detail how this additive manufacturing can be an important contributor for Industry 4.0. So if we see what is additive manufacturing, so here one picture is shown where eventually we want to make some 3D objects. So we start with 3D CAD model of that part. Then using designs tools, we convert that model to machine identifiable language STL file, and the slice the layers and generate the tool path. Then this information or these commands, basically they are fed to the 3D printing machine, and the machine, based on the given command, it prints your object in layer by layer manner, and finally the entire shape is obtained. So if we define it, the aim, it is making objects layer by layer from 3D CAD data. And of course we'll see that it is different from material removal in traditional subtractive manufacturing, because in this process we are adding the material instead of subtracting it. So typically 3D printing or additive manufacturing processes are identified as what you see is what you build kind of process, right? And as I mentioned, here we follow up a bottom-up approach where layer by layer build off of the entire component is being obtained. And this additive manufacturing can produce parts of different materials, including metals, plastics, and composites, and even ceramics. So this slide shows you a basic difference between additive and subtractive manufacturing. We all understand and know that in subtractive manufacturing, we start with a given block of material, then using one or several subtractive manufacturing processes or its combination, we finally manufacture our desired object. While doing that, we witness a lot of material wastage as well. On the other hand, additive manufacturing, we start with material in the form of, say, powders or some kind of feedstock, and using a single piece of equipment, which we call 3D printer or additive manufacturing equipment, based on the given design data, and we prepare the given shape in the layer-wise manner from bottom-up approach. And this way, the final wastage of material is very little. So in this sense, you can see not only the wastage of material can be minimized, but also the number of equipment requirements can also be minimized. Both of these serve as a reduction of energy and reduction of resources. And that's why this additive manufacturing is very much based on the concept of green manufacturing. So regarding additive manufacturing, it is being said that it provides tremendous unmet flexibility in form and function, right? We learned that additive manufacturing process converts digital design data straight into physical objects. And at the same time, it opens up new opportunities for manufacturers, increasingly replacing some components of traditional manufacturing and allowing new geometry and internal structure for lighter, stronger, and more cost-effective designs. So we'll see these very soon. Then throughout the world, we could see that there is significant increase in market for additive manufactured parts. This is a projection and past history show for 3D printed parts in US $1 million. And you can see that right after 2015, there is a rapid growth in the market share and by 2025 it is projected to cross even 10,000 million US dollar, right, which is significant for 3D printed part. So of course there is worldwide focus on additive manufacturing, and in India also we are focusing on that, and we need to match the speed with which the other part of world is progressing in this area. This will help us to indigenously produce AM components, and then it will also help us to innovate process design development, and to process to develop capability to process various materials, and eventually it will impact our Indian industries. So we must now understand what is the the main region this additive manufacturing technology is growing so rapidly, right? So we must understand its benefits. So the very first benefits, it is based on concept of green manufacturing, which I already mentioned to you, that it provides much reduced material waste and energy consumption is also very little. Then tooling reduction, because it uses a single piece of machine. It is shown here, a single piece of machine. Then utilizing CAD model and feeding data from the CAD model to the machine, you get the finished product, right? And this way, if the CAD model is ready, the printing of that part may not take more than few hours. So you see, this way, it can provide a single piece, particularly in serial production, a part very quickly. And that way it reduces or shortens the time to market to launch, and that way inventory reduction could be significantly achieved. Then since it is based on 3D CAD data and utilization of a piece of 3D printing machine, so we could perform prototyping and testing right at the concept, and that way we can come up with several potential designs and quickly print those designs and check the prototype printed and then finalize the design. So this way it is a kind of very rapid conversion of your design and prototypes to a final part. Then because of material addition kind of process in this technology, complex shape is not an issue. We can manufacture any complex shape, and this is the most important contribution. Not only that, we could manufacture lattice structure, and by doing that, and even by doing topology optimization, we could achieve significant light weighing in the component without sacrificing on the performance. Here example is shown like the complex heat exchanger. It is manufactured as a single piece using this process. Then some hydraulic component with complex internal geometry was manufactured as a single piece. Then some tools with conformal cooling channels was manufactured. Then using design innovation and topology optimization, we could achieve significant weight reduction. One example, classical example is cited about bracket used in aircraft. Original old design was 2 kgs, but with additive manufacturing and with topology optimization, we could manufacture the same part with 300 grams, and there is no compromise with performance. So this process is basically, it is here we have freedom of design, and which eventually leads to manufacturing for design concept. So you design anything and it will be manufactured. This is the idea. You can see some of the examples here. Then there are many applications where we need graded structures or graded properties. So in such kind of requirement, whether it is biomedical implants or hybrid manufacturing, these are very important contribution, because only this additive manufacturing can potentially do that. Using conventional manufacturing, it is just next to impossible. So after this slide, I like to mention a few things. People always ask that should we completely replace conventional manufacturing with additive manufacturing, or better say, what are the opportunity where I can potentially use AM instead of conventional manufacturing. So these are some guidelines where if you use additive manufacturing in place of conventional, it will provide you benefits. Like say, when we require improved functionality in terms of we want light weighing, we want conformal cooling channels in some tools or material reduction, then we should definitely go for additive manufacturing. And some parts here you can see some engineering parts are shown, complex shapes, parts having some lattice structure for light weighing, as well as sandwich kind of structure. You can see some parts with conformal cooling channels, complex parts for significant weight reduction. And such thing as a single piece, only additive manufacturing process can provide. Conventional manufacturing is just not possible. So in such kind of applications, we should definitely go for additive. The next opportunity or next guideline is that when we see that there is a very complex part and its manufacturing using conventional is very costly affair, then in that case we should utilize additive that will provide us significant economy. For example, complex structure shown here, these are just very expensive and time consuming process to manufacture by conventional manufacturing. In this scenario, additive can definitely provide significant benefit. So here we can again go for additive. Then if we want to save assembly cost, some complex parts using conventional manufacturing requires assembly or welding or joining of several small sub parts. So in that case, it takes time and it increases your cost also. And many times it is just not possible by conventional to manufacture such parts. So in those kind of scenario, additive can definitely come into picture, and it will provide again significant reduction in assembly cost. Some parts you can see a fuel nozzle and some complex part. So you can very clearly see from these slides. Then the fourth opportunity is there when we want to aim for material saving in case of say expensive material like superalloys or some other kind of expensive material. So using lattice kind of structure, we could save the material without compromising on the performance. Here example is shown some kind of lattice structure being inbuilt in the bulk material. Then lattice structure density was decreased from 24 to 4% without sacrificing the material performance. Then some bulk part and sandwich kind of structure with lattice structure. Here you can see engine manifold, and then you see using lattice structure built in between. Significant weight reduction is possible as well as material saving is possible. So this is another potential guideline where additive can definitely provide much better flexibility and opportunity. So as this topic is based on metal additive manufacturing, so I'm not going to talk about additive manufacturing of other materials like polymers, ceramics, composites. I will directly come into metals part. So for metal additive manufacturing, there are basically two technologies. One is based on powder bed fusion, where we start with powder metal and using a heat source like laser or electron beam, we selectively melt the powder particles in the powder bed and allow it to re-solidify to provide us a consolidated track. And this way, layer after layer buildup is followed in vertical direction, and then finally a final shape is obtained. Example is shown here. This is metal powders and its SEM image, and using the machine we get this complex part in layer wise manner built up. The other technology is based on powder delivery, where the powders are not spread in the form of powder bed, but it is actually simultaneously fed from a coaxial nozzle from where laser is fed. And this technology is known as directed energy deposition, DED. So these are two main technology available at the moment for metal additive manufacturing. So this powder bed fusion technology, as we can see, one thing, we have a powder bed and we selectively melt the powder bed using some thermal energy source. The thermal energy source could be laser beam, and the process in that case is selective laser melting or laser powder bed fusion. The other source could be electron beam. In that case, it is electron beam melting or electron beam powder bed fusion process. So one schematic is shown here. You have a given powder bed or powder layer, and you are applying your laser selectively according to the tool path design, and wherever it crosses the powder bed, it creates a melt pool, and that melt pool solidifies to give you a solidified track. And then this layer, one layer is created, then again you do the same process for second layer, third layer, fourth layer. Likewise, you finally get your final product. So typically these layers are something about 50 micron in height. So suppose you want to get, you know, a 100 millimeter height of the object, you can very easily find out 100 millimeter divided by 50 micron. These many number of layers would be required to get your final object. So this is the basic thing. I like to show you one animation after that. So locally, if we see when the laser is operating on a powder bed, we are obtaining a melt pool, and laser is traversing from left to right. So this left side is already solidified layer. This is the local melt pool where the laser is falling. And then this laser is traveling toward the right side, and it is interacting with the remaining loose powder. And this way, we obtained convert the loose powder in the powder bed to melt pool, and then melt pool to a solidified layer. So this is how we get the joint kind of, you know, welding. And this is something like, this is why the part density produced by this process and its strength is as good as a welded joint. So let us see this animation. This will show you the process, how this metal additive manufacturing process work. So this is the CAD model development of an engineering part. It is impeller in this case. In a single build, several such impellers can be produced. So that advantage we are taking. They are setting up the machine parameters. Then the machine started. So say first layer of all 12 impellers are being created. Laser is being falling on the powder layer. See the process here. After creating the powder bed, laser will operate on this powder bed according to the tool path. So this way, layer after layer is being created. And you will see that finally your final printed object is ready. So the parts were printed and they are now being removed. After this, some post finishing operation will be done to remove support structure and to provide surface finish. And then your parts were ready to use. So in an industrial site, there are several such machines put together, and for example, for processing different size or different material kind of requirement. And all these machines are connected through your CAD design center, where the information is fed to these machines centrally, and according to your need and all, these machines can operate and provide you your additive manufactured part. More examples of machines, such machines installed in industrial site. So let us see a concept of smart manufacturing and what are its various components with regard to Industry 4.0. So you can see this schematic here. This is a busy slide, but I will explain it. See, the smart factories represent a new generation of the production system in the concept of Industry 4.0, and it support advanced technology such as additive manufacturing, cyber physical systems, big data, Internet of Things, and cloud computing. Okay. So IoT here provides information from all physical objects through a wireless or network connection. And CPS, cyber physical system, it shares information regarding all machines, utilities, and storage system, and controls them autonomously, right? So in this way, CPS technology help us to effectively improve the manufacturing process in the concept of smart manufacturing. So let us see here. We have, for example, customers, right? And even from home, we can demand on-demand manufacturing, right? And this information is being fed to, say, smart factory, right? And real-time machine communication. Then basically here it involves a lot of things like autonomous robots design section, then collaborative manufacturing, either using single machine or combination of several machines, then analytics for that. Before that, we need to sort out for given product requirement what materials is most suitable, or sometimes user can provide you material as well. So using that, you can decide again whether additive manufacturing to customize product, or you that part, if it is not manufactured by additive, can we go for collaborative manufacturing. And based on that, finally you will have a finished product. Then instant analytics part is very interesting because it involves a lot of information based on your past experiences, on past data available on manufacturing of such similar parts. And if some data analytics and Internet of Things information is required to do some cloud computing, this will be fed to this instant analytics parts, and then accordingly it will choose the material, process, and process parameters, and that way design optimization and then part optimization, and finally provide you the given part. Okay. And then once you manufacture such thing, then it is ready to deliver to the customer. So this is something like involvement of several aspects, and a good synergetic approach is required, that we can say. So now from here we saw something like a concept of cloud manufacturing, right? So this refers to the processes that are highly service oriented and can be modified online. And this technology gives the opportunity to integrate many machines in a factory and control them online. The outcome of this combination is that a user-specific product can be produced within each machine. And let us understand this by an example. Suppose a customer orders a given geometry to be purchased. So after assessing the design tools provided by a factory, uh, they can change the materials, colors, and other aesthetic features of their desired product. And at the same time, they can check the availability of the materials, machines, and transportation system, so that they can assess in how much time I can get the final product delivered to my doorstep. So these are something like on demand driven kind of requirement. And more detail, I like to show you a flowchart of cloud manufacturing and various involved activities. For example, you can see uh, the first thing when you get an order, you start with scheduling, design, and resource description. Then you start to think about whether you want to use rapid technology, like say rapid tooling, rapid manufacturing, rapid prototype typing, or some other technology, whether it is additive or some combination of several manufacturing processes, uh, like that. And if that is being decided, then you need to think about some data analytics for choice of optimized parameters and even optimized design. And then of course, on other hand, your stakeholders or customers is there to choose their final material, final size, or some aesthetic design kind of thing, final delivery time, and all those things can be actually. So this is how this integrated cloud manufacturing works, right? And if I want to see architecture of the CAMP system, which is in cloud-based additive manufacturing platform, you can see this is here. We have service requester, then a platform provider, which actually deals with services and description, and at the back end it deals with machine, material, sensors, software, data, and know-how. Okay, so this is your service provider. So there are three major stakeholders in the cloud. One is service provider, the one is service requester, and the third is platform provider. And all these three need to integrate properly. And this is the very basic design concept of CAMP, right? So service providers connect their printers and other printing resources to the cloud and upload resource capability and know-how. The service requester explore the options they have and find most suitable solution for their task and make orders. Now the platform provider provides cloud computing and storage facility and construct the platform to serve as an online marketplace. So I think this you can understand very well. This Internet of Things, for example, is now working. For example, say we have Amazon, for example, or Flipkart, right? So they are service provider basically. So here in the similar concept is brought for this CAMP as well. So if we let us see now how the information flows in additive manufacturing processes, basically for cloud-based 3D printing services. So let us see first basic information, which is shown at the bottom. We have a user, then based on cloud availability and all, we could select the part and corresponding CAD file. Then this is information is sent to the operator. In that case, we have which will operate the machine and appropriately select the optimized parameters and finally provide you the printed part. In more detailed manner, let us see the first thing. First is process planning and second is design. And in between, based on the know-how, these two are well connected. So requirements are like say what process, what material, what printing parameters. Then on design side, it's 3D model and it's machine identifiable, tool path generation. So these two finally, after our know-how, will finalize and then set the G code. I sliced contour data to the printer and it will print the part. So this is very simple to understand, right? So I think I don't have to focus much on this. This is something like a very clear, steps followed for how the information can flow in such cloud-based additive manufacturing. So if we just want to highlight the advantage of IoT-based additive manufacturing, So we can see from our previous discussion, it provides a tremendous creativity. Then design products with fewer and more complex parts possible. It preserves energy by obviating production process, decrease in wastage, and faster deployment of Industry 4.0. And of course, we have opportunity to reduce waste, to topologically optimize the part, and all the opportunity what we already saw in the case of additive manufacturing. So after this, I like to show you the typical interrelation between some key features, which are actually requirement for any manufacturing process, and the advantages of additive manufacturing for those key features. For example, we have key features for any manufacturing processes where we want more and more better solution. Like say cost, we definitely want less cost. Time, we would definitely want less time. And flexibility, we want several design flexibility. So in all these three attributes, if we see, the additive manufacturing is fitting very nicely. For example, cost, it provides less material wastage and less machine tools cost, right? Then in flexibility, we have various properties in a single part and complex parts possible. In time, rapid process, right? In between, you see that it also provides flexibility, that between cost, time, and even flexibility using rapid prototyping and spare parts and on-site manufacturing. All this flexibility and all these further attributes, it aids to the benefits of additive manufacturing to come out even more clearly. And this is the way we could take a full, or complete benefit out of additive manufacturing. Then one very important aspect comes into picture, that whether this additive manufacturing is sustainable or not. So of course, to assess its sustainability, we need to assess, or we need to evaluate this process under various aspects. And we all know that reduction in energy and material consumption and transportation packaging system for different life cycle analysis methods have been performed on additive manufacturing processes, and in order to make them more sustainable regarding their economic, environmental, and societal impact. And for example, there are different attributes under economical aspects, under environmental aspects, under societal impact aspect. Those are being evaluated, as well as those are being tested for new parts. For example, on economy side, the market evolution of a given part, then its application, its supply chain, and then production cost, machinery cost, then process productivity, these all need to be evaluated. On environment side, we need to evaluate resource consumption regarding materials demand, process life cycle energy, waste management, right? And pollution control. On societal benefit side, we need to see about labor development, product quality, public acceptance, healthcare improvement, and ethics, and all those things. So in most of these attributes, additive manufacturing, assessment is coming positive, and that makes it as a sustainable process. And because of that, there are several benefits attached to additive manufacturing, which are again sustainable. We already saw that AM introduces numerous significant change in product design, materials processing, manufacturing process, and supply chain management. And compared to traditional production such as machining, forging, finishing, casting, etc., additive provides a great opportunity in sustainable production. And some of the advantages I like to list here, we can see those. For example, the less raw material which is required in the supply chain process, right? Now, higher resource efficiency in manufacturing processes, reduce consumption waste material and pollution in the manufacturing process because it uses a single piece of equipment, higher efficiency and flexibility in product design, the lower number of transportation processes, and reduced carbon footprint. This is again, I mentioned that one single piece of machine can do all the jobs for you. Then it is decentralized and close to consumer manufacturing. Then shorter supply chain and more localized production using innovative distribution methods and collaboration. And then extended product life by novel technical methods such as remanufacturing, reusing, repairing, refurbishing, and sustainable socio-economic production. So all these advantages make the additive manufacturing quite sustainable. If we see the cost versus production speed forecast, for example, in 2013 and now up to 2000, after 10 years 2023, we could clearly see that the cost is becoming 50% cheaper, right? And at the same time, the productivity has improved 400 times. So you see, the limitation, people say that additive manufacturing process is slow compared to mass production system. So in that regard, also improvements are coming up, and the other issue that it is expensive affair. So there also the cost is coming down with with time. And basically the ongoing research activities and what I mentioned, utilization of IoT and cloud-based manufacturing into additive manufacturing system. So that is also contributing to such reduction in cost and increase in productivity. So after looking at this, I like to point out some potential application of additive manufacturing, and particularly I would focus on metals, not on polymers and other ceramics. So when this additive manufacturing technology has came into industrial prospect in 2014, something like that. So that time the forecast was something like we only know 1/3 or less than 1/3 of its utilization. The remaining is still in the iceberg, immersed in the ocean. And down 6 years down that 2014, we could see that many of that emerged applications already came up to the surface, and we are actually looking at applications. Earlier it was applications only for models and prototype development, some pattern development, and something like plastic aircraft part. But nowadays we could see that additive manufacturing application in medical implants, in molding industry, in custom prosthetics, in aircraft industry, in electronics industry, in integrated electronic circuit industry, then automotive industry and all. And they are coming up, and then there are many unimaginable applications which are still need to be explored. So this way I can say that this aim is heading towards a very bright prospect. There is no doubt about that. If we see on the metals part currently, we could see from this slide that there is several potential industrial applications, starting from aerospace, automotive, tooling industry, hydraulic industry, repair industry, biomedical industry, where this metal additive manufacturing can play a very significant role. You can see different industrial application and some typical parts, the photograph of those parts already being made. There are tons of such applications. So now there is wide acceptance that yes, this additive manufacturing can be a very important contributor to Industry 4.0, and people are working towards to make it something like more IoT enabled and cloud enabled kind of manufacturing systems. So it is very nice to see all good things about additive manufacturing, but we should also identify and recognize the typical challenges and limitations. For example, there is some imperfections when we create layer-wise build-up. For example, voids and porosity between the layers, which deteriorate the interlayer bonding strength. So that way, mechanical performance of such parts become poor. So this is one of the important aspects, how to address these defects formation so that they can be minimized. So here, a lot of research at physical understanding of the process is required, which is very significantly ongoing research throughout the world, how to minimize defects. Then second aspect is cost. Right now, as I mentioned, the equipments are expensive. At the same time, the material like powder materials are also expensive. But as I also said, with time and with more research into these aspects, the cost of machine as well as cost of powders and overall cost of the part is coming down. Okay, so down 3 to 5 years, we will see that its cost is further reduced. Then production time, it is being said that additive process can be better suited for serial production or a small batch production, but for mass production it is not really suitable. Yeah, I agree to that, but again, with research, more research into build platform and building time, this can be also addressed so that at least to acceptable batch production size could be achieved. Okay, then limitations on materials. Right now, it is possible to use metals and some polymers in AM technology. Polymers domain is quite well developed, but metals domain is not well developed. We currently have only a limited metals materials available in the material portfolio, but with more and more research in alloy and material development in metal side, more material will be added to this portfolio. Then the other limitation is size limitation. AM systems are limited regarding production of parts bigger than their build chambers. Of course, here large size additive manufacturing is being researched through. So as I mentioned, in all these challenges and limitations, there is significant research going on throughout the world, and yes, definitely some of these challenges can be reduced. I don't want to say that additive can completely knock out traditional manufacturing methods, and I don't suggest that also. Instead, I suggest another view that additive can be combined and integrated with the conventional manufacturing so that we could achieve efficient production of complex products. Okay. So in this regard, I can now broadly highlight various research opportunities. There are huge research opportunities in various aspects. For example, as I mentioned, one research can be on minimization of defects and understanding the microstructure of the additive parts. Then improvement in build rate or productivity, then stresses and how to minimize those, then improvement of surface finish, then manufacture of complex part and lattice structures, new and novel materials development, then manufacturing with multi materials, and manufacturing of functionally graded structures. Then on design side, there is a huge scope on part design, CAD side, tool path generation, and on application oriented research, there is huge applications. You can choose any industrial application and try to explore what are the potential parts which can be additively made, and whether there is economy lies in producing that part with additive process or not. Apart from this, there is a huge scope on IoT and cloud-based systems development itself, and where not the role of mechanical engineer or even materials engineer comes to picture, but role of something like computer engineer and systems engineer is better required. So that side also there is a huge scope. So I think with this, I'm coming towards the end of my talk. I like to end my talk with this slide to show you industrial Internet of Things picture about that. Okay, and as I mentioned in this, additive can be one of the important contributor. So some references I like to mention. These were references, and acknowledgement to our project funders, DST, Imprint, and ISRO. And with this, I end my talk. Thank you for your attention, and I can take up questions and discussion now. Thank you very much.
Thank you, sir. Any questions from the participants? Participants, any questions? I think no questions from the participants.
Yeah, if they have some questions later on also, I can reply in email. If you can combine all questions and send it to me, I can reply over email.
Sure, sir. So any other thing you want to show, or this?
No, from my side, it is okay. I'm done. Okay. So.
Okay, sir. So then we can wind up, sir.
All right. Sure.
Okay, sir. So thank you very much once again, sir. So let me invite Mr. Eldos Paul, sir, for the vote of thanks.
Thank you, sir. Thank you, Dr. Shanmush. So even though there are actually no questions from the participants, I think all the participants have benefited from the very relevant topic, additive manufacturing. And I believe being the lead in the additive manufacturing group at IIT Kanpur, we got some very authentic information regarding the additive manufacturing, especially in sustainability application, and also the research opportunities regarding the in the same field, that is additive manufacturing. Okay, so on behalf of Vishwadi College of Engineering and Technology and Mechanical Engineering Department, I extend my great thanks towards Dr. Arvind Kumar for having you as a guest or the speaker of the day, and thank you very much, sir, for your valuable class.